previous video, we looked at a model for epidemics in which we had three classes of people: susceptible, infected, and recovered. And we allowed people to transition between those states based on certain simple interactions. So when it's susceptible and infected people interacted, there was some probability that they would transmit the virus or bacteria or whatever was carrying the disease. And so we had a transmission probability P that we used. We had a contact rate parameter C, which represent the number of types of interactions that you would expect for a person to have. We had a ratio I over N, which took the number of infected out of the total number of people. And we used that as an estimate for the probability that when somebody interacts, they're actually interacting with someone who is infected. And based on that, we determined that the number of people who should get sick on a given day should be the product of PC times SI over N. And we had similar events for recovery. In that case, you didn't have to interact with anybody else to recover. Just given the number of sick people, we had a rate parameter R, which had units of 1 over days, and that would tell us how many people would recover on a given day. And then we also allowed for the possibility of losing your immunity, which means when you're infected and then you recover for some time, you can't get sick again. And so we're placing people in this recovered category where they had immunity. But perhaps over time that immunity could diminish, and so you could have a parameter L for the lost immunity rate in units of 1 over day. Now, that was a completely deterministic model, and we did a whole bunch of analysis with this. We looked for fixed points, we classified the stability of those fixed points, and we saw that depending on the value of L, you could either have a disease-free state where nobody was sick in the long run, or you could have an endemic state where the disease stuck around indefinitely. What I want to do in this video is I want to look at how we can modify that model to make it a stochastic model, where we allow for randomness in the fact, and this will take into account the fact that, well, people don't behave the same way every day. Sometimes they interact more often. Sometimes they interact less. Sometimes when you interact, you get lucky and you don't get sick. Sometimes you get unlucky and you get sick surprisingly. And so we can tweak this model by just shifting the interpretation. We don't even have to really change the equations at all. So before we were thinking about sort of the average number of people who would get infected or recover or lose immunity. However, we could easily modify this by thinking about this as a probabilistic process. Each of the S people in our population who are susceptible, well, on average, we would expect S times PCI over N to get sick. But we could also think of that as for each person we flip a coin. And on average, again, we'll expect a certain number to get sick, but each person would therefore have some probability of getting sick. And if you look at the units, then the appropriate probability that would give us the correct average would be PCI over N. And so if you could imagine flipping S coins, one for each susceptible person, where each coin has a probability of coming up heads, meaning you get sick, with probability P times C times I over N, then we would have, on average, the appropriate number of people getting sick, but we'd have some probability of more sickness and some probability of less. And you could do the same thing for recoveries. Again, you could imagine flipping a coin for each infected person, where the probability that you get better is R. And if you do that, you'll see that on average, R times I people get better on each given day, but again, sometimes more, sometimes less. And for lost immunity, you could flip R coins, one for each recovered person, and have probability of success L. All right, so let's actually look at how we might implement that with the computer. So I'll bring up Octave. And so first things first, I've set up the parameters of the model. I just chose some particular values for the probability of transmission, which I guess I was calling E when I wrote this, C for the contact rate, L for the lost immunity rate, and R for the recovery rate. And don't worry so much about the parameter values. You can easily change these to change the dynamics. I just want to choose some generic parameters so that we can see sort of what types of behaviors we end up with. All right, we have our update rule, which incorporates the model that we built earlier. This is basically identical to what we did before. And we're going to start with, it looks like everybody but one person is going to be healthy, and that one person is going to be sick. And I'm going to also compute the fixed points that we computed earlier and add those to our plots, because I want us to see how that deterministic model correlates to this random model. And then for our simulation, what we're going to do is we're first of all going to run an experiment 50 times. Now this is going to take a little while, so I'm going to actually update the plots as we go, so we'll kind of see the results as they come in. But we'll initialize the system with our population of all but one person susceptible and one infected person. And then in each step, we'll flip a coin for the number of people who are going to go from state S to state I. With again, there will be S susceptible people, so that's the number of coin flips, and then the probability of success will be the remainder of that term. And then we can do the same thing for I and same thing for R to determine how many people leave each state. And then once you've got all of those, once you've counted up how many people are switching between states, you can update the new totals and then plot the results and then repeat. All right, so that is the code. Let's look at what the results look like. All right, so here we go. I've plotted the fixed points as dashed lines, and so you'll notice I'm getting curves added one by one. And so the green is the recovered, the blue is the susceptible, and the red is the infected. And something interesting is happening here that we did not see in our deterministic model. Now, in our deterministic model, we would basically have some sort of sharp rise of the number of infected, then it would go down, and it would approach a fixed point. Maybe there was a little bit of oscillation around the fixed point, but it would always end up approaching the fixed point. But here, now that we've incorporated randomness, we can see that there's actually two different types of behaviors going on. You can see this in the blue curve. Notice that, first of all, the initial drop in the number of susceptibles corresponds to the initial rise in the number of infected people, and it doesn't always happen at the same rate. And that's a result of the fact that, well, when you have only one person who's sick, when they actually get the next person sick has a great effect on when the disease spreads. And as long as the number of sick people is small, that early stage of the epidemic is very, very volatile. It's going to be very much dependent on how people interact and how unlucky we are with the rolls of the dice, so to speak. But once a lot of people get sick, then you'll notice that we essentially get the same behavior. And that's due to a property called the law of large numbers, which basically says that the variation in a random process is small when you have a large number of coin flips, say, right? So if you flip a coin 1,000 times, you're not going to see a lot of variability in the number of heads relative, percentage-wise of the total number of coin flips. And the same thing is true here. Once a lot of people are sick, the behavior seems relatively predictable. However, over time, you'll notice the infected people peak, right? We have a rise in infection and then that starts to decay, although the actual time of that peak varies from one run to the next. That corresponds to a drop in the number of susceptible people. And then once the people are no longer susceptible, well, there's no one else to get sick, or at least not many people to get sick. And then the number of infected starts to drop. And the recovered also is growing at the same time. However, if you look at the blue curve, it's the easiest to see here. You'll notice that some of the time, it looks like, even here, once it happened early on, sometimes it happens later, that it actually looks like it asymptotes to 1,000, which was the full population. So in this case, it looks like we ended up with everyone susceptible relatively early on in the epidemic. And then these other cases, later on in the epidemic, everyone seems to be susceptible again. And if you look at, again, recovered, here we have a spike for most curves, but every once in a while, the number of recovered goes down to 0. And one time, the number of recovered went down to 0 early on. It's the hardest to see in the infected, but actually that's where all the interesting stuff is happening here. So let me see if I can zoom in on that just a little bit. And this is where we see what the reason why this was happening. So notice here, the number of infected actually dropped down to 0 in the early stages of the outbreak, right? And that's like the scenario where one person is sick and we get lucky, they don't get anyone else sick, and then they get better. Well, if that happens, there is no outbreak. Now, in a deterministic model where we allowed all of the variables S, I, and R to be continuous variables, that was never going to happen. You would always, always, always have an outbreak. But when we account for this randomness, then we see that there is some probability that even though we're in this very dangerous scenario where an outbreak could happen, it doesn't always happen. So there's some potential that the outbreak could die out in the early stages. And then if you look at the tail, when the number of infected gets relatively small, you can see there's some chance that you're actually going to drop down to 0. And so this is after the peak. We've got a low number of infected people, so we're in our endemic state. But every so often, we may do a good job of isolating those people. They may not interact. And as a result, the number of infected may, again, if we get lucky, drop down to 0. And the result is that there are no infected people left. And so there's no one else that can possibly get sick. And once that happens, once there are no infected people, you'll see is that the number of susceptible people will rise as the number of recovered people fall. So as people are getting better, we see that the number of susceptible people approaches the entire population. And so essentially the population as a whole loses its immunity due to the fact that people are no longer being exposed to the pathogen that caused this. So that's really important to recognize, and that deterministic models don't account for these rare events. By looking at the typical behavior, we may miss out on the fact that, well, there's some chance that the outbreak stops in the early stages, and there's some chance that the pathogen ultimately goes extinct once we are able to get all of our infected people to recover. And so when you're modeling epidemics, incorporating randomness can be really important because they can allow us to estimate the probabilities of those things. Right? We can run this simulation many, many times, and we can count up how many times did the outbreak actually happen. Maybe there's a 90% chance of an outbreak, which would be bad, but that fact that there is a 10% chance that no outbreak happens, it might be good news for us. Similarly, we can ask the question of what's the probability that ultimately we end up in the endemic state? In the deterministic model, we always end up in the endemic state. But in this stochastic model, there's some probability that the epidemic dies out. And in fact, you could say, what is the average amount of time it takes before we're able to eradicate the virus? And what's the average number of people who get sick before that happens? So there's a lot of different possible behaviors that you can see here. And we can't really explore them unless we're able to incorporate randomness into our model. Now, the last thing I want to highlight here is notice that when we do see oscillation in this model, it does oscillate around the deterministic fixed points. So the blue curve seems to be oscillating around this blue dashed line, which is the fixed point we calculated analytically using our deterministic model. Similarly, the green curve most of the time is oscillating around this green dashed line, and the red as well. So the deterministic model does give us useful information, and it can explain some of the behavior in the stochastic model. But sometimes by trying to make things deterministic and allowing variables to be continuous when actually the number of people who are sick or recovered or susceptible should be an integer, sometimes those sorts of approximations do change the behavior. And so it's good to explore stochastic models as well to make sure that we're not missing something important. Now, this phenomenon that we see here, where sometimes when the numbers are small, we get a radical change in behavior, is sometimes called the Addo-Fox effect. And that's a reference to the fact that it's also observed in predator-prey models. And it has the idea that sometimes what you'll have is a scenario where the number of foxes in your population model gets really, really small. Atto is a prefix. I believe it's like 10 to the negative 18th. There's some astronomically small quantity. And so in a model, you may see that your population of foxes drops to 10 to the negative 18th. Well, in practice, if you have 10 to the negative 18th foxes, that's the same thing as no foxes, right? You have to have an integer number of organisms. But a deterministic model doesn't know that, a continuous model that is. And so when you do a continuous model, you can see that population of foxes drop down to close to 0 and then spike back up again. Whereas in a stochastic model where we restrict the variables to be integers, we would see that that behavior doesn't happen. And so you allow for extinction events that would be missed by the deterministic model. And so that's exactly what we're happening here. Instead of an Atto-Fox, I guess we have an Atto infection, but the same principle applies. The deterministic model might predict that you have half an infected person, in which case it still considers there to be some possibility of people getting sick. But in reality, once less than one person is infected, well, the disease should be eradicated and your population should be in the clear. All right. So that's a basic epidemic model. And you'll notice in this case, we didn't really talk about space at all. We assumed basically that every person in the population is just all in some region, and they all interact with each other with equal probability. And so in the next type of model we look at, will allow for spatial variation and spatial movement, and we'll also see that that can lead to some interesting epidemic models as well.